Good evening, good morning. This talk has to do with some work that I did jointly with Serge Abiteboul starting in the late 80s on Datalog with forward chaining semantics. Serge and I are really fond of this work, and I'd like to thank the Gems of Pods committee for this kind invitation and for giving us the opportunity to review this work for you. So we were motivated for this work by what we perceive to be a crisis of the declarative approach to negation in Datalog. So there were difficulties coming up with semantics beyond the well-accepted stratified semantics, and the declarative approach seemed to hit an expressiveness ceiling with the fixed point queries. In contrast, forward chaining had already been adopted in active databases, production systems, expert systems, but had not been studied formally. And so at PODS 88, two papers independently proposed as an alternative the forward chaining or fixed point semantics to Datalog with negation. And this was very aptly captured by the title of the second paper by Kolaitis and Papadimitriou, which was called "Why Not Negation by Fixed Point?" So this gave rise to a line of research explored in a sequence of papers, and this is what this talk is about. Now, the results of the research consist primarily of a family of Datalog extensions with forward chaining semantics that can very naturally incorporate features such as updates, value invention, and non-determinism. And this also provides a formalism for a unified formalism for expressing the main classes of queries, including fixed point, while, and all computable queries. So in terms of expressiveness, one can say that Datalog has been unchained. So I'd like to briefly mention these two very important classes of queries, fixed point and while. I won't have time to go into any details, but essentially they are extensions of first order logic with recursion. Fixed point is included in p-time, while is included in p-space, and they coincide with p-time and p-space on ordered databases. Now, Datalog emerged in the early 80s as a specialization of logic programming to databases. The main difference being that Datalog has just relations and no functions. So the prototypical example is this two-rule program for transitive closure. Okay, so G is a graph, and the program produces the transitive closure in relation T. So in its simplest form, in its basic form, Datalog consists of positive queries or unions of conjunctive queries extended with recursion. But in time, Datalog was extended with numerous features, and the term Datalog has come to be used generically to designate the entire paradigm. The semantics of the basic Datalog is very simple and elegant. It's a declarative semantics based on minimal models. So the idea is to associate to the rules of the program corresponding implications. And it can be shown that this resulting set of sentences has a unique minimum model that includes the input database. Now, how is this minimum model computed? Well, there is a counterpart procedural semantics based on fixed point or forward chaining, which consists of firing the rules up to a fixed point. And it turns out that there is a very nice connection between the two semantics. There is a unique minimal model, a unique minimal fixed point, and the two coincide. And for this reason, Datalog has been called the Garden of Eden of semantics. Now, as soon as negation is added to the language, there is trouble in this paradise. So consider this program where the last rule is meant intuitively to produce a complement of the transitive closure. Now, the problem is that it's not easy to give a model-based semantic to this program because there's no longer a unique minimal model. There are many minimal models. So a declarative semantics would need to specify an intended model among all the candidate minimal models. However, there is a very natural but restricted solution, which is a stratified semantics, which applies to a class of syntactically restricted stratified Datalog programs, which prohibits recursions or negation. And it turns out that for stratified programs, there is a well-defined way of parsing them so that whenever the negation of a relation is used, the corresponding relation has previously been computed by other rules of the program. So in the case of this, the program above, the first two rules compute t before the negation of t is used in the third rule. And with the semantics, the program computes the complement of transitive closure. Okay, so how about all Datalog programs with negation? Well, the consensus has converged towards a very elegant semantics called the well-founded semantics, which is based on a three-valued minimum model where facts can be true, false, or unknown. And this has also a procedural counterpart, which is based on alternating fixed points. In terms of expressiveness, this expresses a fixed point queries, which emerges as an expressiveness ceiling for declarative semantics. Okay, so I'd like to illustrate the fixed point or forward chaining semantics using Datalog, and things work basically the same for all extensions. So consider this program for transitive closure. So in the forward chaining semantics, the program is evaluated in stages. Each stage consists of firing the rules with all valuations that make the body of the rule true in the current stage. The body is the right side of the rule, and the head is the left side of the rule. So if G consists of the graph on the right, then in the first stage, G is just copied into T. The second stage adds the pairs of nodes at distance 2. The third stage adds a pairs of nodes at distance 3, and at this point, the computation converges. Now, if negation is present, forward chaining works in exactly the same way, except the negative literals have to be true for a given valuation in the current stage in order to fire the rule. So if we look at this program, it's pretty easy to see that the closer relation finds all the four tuples x, y, x prime, y prime, for which the distance between x and y is strictly less than the distance between x prime and y prime. Now let's look again at this stratified program defining the complement of transitive closure. So one might wonder if this can be simulated using forward chaining. So in order to do this intuitively, the application of the third rule would have to be delayed until the first two rules are saturated. And on the face of it, there doesn't seem a way to do this with forward chaining semantics because there is no explicit mechanism for controlling the computation. However, it turns out that this can be done with a little trick which takes advantage of the timing in the firing of rules. So this consists of adding two relations. One is called old t, the other is called old t except final. Old t is going to be identical to t except one stage behind. And old t except final is going to be the same except when the last stage has been reached. So it's going to be fired as long as the last stage has not been reached. And this is checked by this condition here. So old t and old t except final are going to be the same except when the last stage has been reached. So to check that the last stage has been reached, it's enough to detect a difference between the two relations, which can be done like this. Okay, so this program succeeds in computing the complement of transitive closure. Good, so this sounds promising, but one might wonder how far it takes us. Well, it turns out that this can be carried out all the way to the fixed point queries. So Datalog with negation and forward chaining semantics expresses all the fixed point queries. And this was kind of surprising, a surprising result because again, because forward chaining does not seem to have the necessary control. Now, suppose that we add deletions to heads of rules. So the forward chaining semantics functions in a similar way. So using similar techniques, it can be shown that Datalog with negation and deletions expresses exactly the wild queries. Good. Now, how about if we want to go beyond this expressiveness and in particular break the p-space barrier to which the previous languages are subject? Well, this can be done in a pretty straightforward way by providing a mechanism for creating new values throughout the computation. And this can be done syntactically using variables that occur only in heads of rules and that are mapped to values outside the current active domain. So for example, if this is in this rule, variable z appears only in the head of the rule. So if R is this relation, an application of the rule is going to produce this T, where A prime, B prime, C prime are distinct new values that do not appear in the active domain. So this clearly allows to take the computation beyond p-space. And in fact, it turns out that with this feature, Datalog with negation expresses all computable queries. Okay, so this is a picture of expressiveness for the languages discussed so far. So all inclusions are strict, except the one between Datalog with negation and Datalog with negation and deletion, which is conditional upon p-time not being equal to p-space. And this uses another result joined with Serge, which showed that while is different from fixed point if and only if p-time is not equal to p-space. Okay, good. So if order is present, then using, again, known results, it can be shown that the two Datalog languages with negation and deletions express all of p-time and p-space. And Datalog with negation turns out to be equal in expressive power with stratified Datalog. All right, so I'd like to discuss another feature which can be easily accommodated with forward chaining semantics, which is non-determinism. Now, why non-determinism? Well, so first of all, there are many examples which are naturally non-deterministic. Some of them come from AI. For example, suppose we want to seat people at a dinner table so that no spouses are next to each other. So this typically has several solutions. So finding one such solution requires non-determinism. Similarly, suppose we want to assign to a paper 3 reviewers without a conflict of interest. This again is naturally non-deterministic. And these are all instances of a pretty general class of problems which consists of finding one solution satisfying specified constraints. Now, it turns out that non-determinism is also present in many rule-based systems, such as active databases, production systems, expert systems, and data-driven workflows. So what is a non-deterministic query? Well, it's a query that on a given input can produce several outputs. And if we place complexity constraints on each of the non-deterministic computations, we obtain classes of non-deterministic complexity classes. For example, if the constraint is that each computation has to be in p-time, this yields non-deterministic p-time. And it's very important to note that this is not the same as NP. NP is a class of deterministic properties. NDBP time is a class of non-deterministic queries. If the complexity constraint is P space on each computation, then this yields non-deterministic P space, NDBP space. Okay, so let's look at some non-deterministic variants. So the basic idea of the non-deterministic semantics is simply to change forward chaining so that only one rule instantiation is fired at a time. Okay, so as an example, consider this program. Let's say that G represents an undirected graph where an undirected edge between two nodes A and B is represented by two directed edges, one from A to B and one from B to A. So if this program is fired one instantiation at a time, it computes all orientations of this undirected graph, where an orientation keeps only one of the directed edges instead of the undirected edge. Okay, so the language, the non-deterministic variant of Datalog with negation and deletion consists of rules of this form, where the head and the body can have multiple positive and negative literals. Now, why multiple literals in the head? Because this provides a very useful mechanism for coordinating, for synchronizing the action of several insertions and deletions. And this can be very useful. Okay, so let's take an example. Suppose that P is a relation with attribute A, Q has attributes A, B, and here is a two-rule program in this language. So I claim that this computes the difference between P and the projection of Q on A. So how does this work? Well, the first rule non-deterministically takes elements of P and places them in the answer. And the second rule deletes elements from the answer whenever it is detected that they belong to the projection. And it turns out that this always converges and produces this difference. So in terms of expressiveness, it turns out that this language expresses exactly the non-deterministic p-space queries. Now, how about the language without deletion in heads of rules? Okay, so the heads consist only of positive literals. Well, one might imagine and one might hope that this expresses exactly the non-deterministic p-time queries, but it turns out that this is not quite the case. So in particular, this language cannot express the previous difference between P and its projection on Q. So this means that something can be must be added to get to P time. One fix is to add universal quantification over the body of rules. So how does this work? An instantiation, so the rule is fired with an instantiation of X. If the body is true for every instantiation of Y within the active domain. So with this additional feature, the previous query can be easily expressed. It's almost by definition. But it seems that this fix is really tailored to this particular query. So, so how far does it get us? Well, it turns out that this is in fact enough. And non-deterministic data log with negation and this universal quantification over the body expresses exactly NDBP time. I want to mention one other variant which is equivalent to this. Instead of universal quantification, the rules are allowed to have an error flag in the head of the rules, let's say bottom. And it turns out that this is also equivalent. The details can be found in the paper. Okay, so if we want to, again, break the p-space barrier, this can be done using the same mechanism as before. So a mechanism for creating new values, which is syntactically specified by variables occurring only in heads of rules. So with this feature, the language expresses all non-deterministic computable queries. So this is the expressiveness picture of these languages. It's worth noting that the the two bottom non-deterministic languages are equivalent to other non-deterministic languages, in particular fixed point logics extended with a so-called witness operator that essentially picks non-deterministically a witness to existentially quantified variables. So this is a nice correspondence. Good. So I'd like to mention briefly an interesting connection with deterministic queries. So it turns out that non-determinism is useful even if we're only interested in expressing deterministic queries. And this is because non-determinism turns out to add expressiveness to the language. This is similar to the impact of order on expressive power. The intuition being that with non-determinism, one can simply construct an order and then use it in the computation. So suppose we have a language, a non-deterministic language NL. So it expresses non-deterministic queries, but some of these non-deterministic queries may happen to produce a single output. So to in fact define deterministic queries. So the set of such deterministic queries expressed by the non-deterministic language is referred to as the deterministic fragment of the language and denoted in this way. So if we look at the previous languages, their deterministic fragments yield p time, p space, and again, all computable queries. So this shows that non-determinism is really very much analogous to order in terms of its effect on expressiveness. Now, if we look at the last or at the bottom result, this may suggest that this provides a language for p-time, which would of course be remarkable and a breakthrough. But it turns out that this is not the case because it is undecidable if a program in this language expresses a deterministic query. Good. So in conclusion, Datalog with forward chaining semantics provides a unified alternative framework within which the theory of query languages can be carried out. The semantics overcomes the expressiveness limitations of declarative semantics, and it can accommodate in a very natural way features such as updates, non-determinism, and value invention. So these are all positive features. There are also some disadvantages. I believe the major disadvantage is the fact that forward chaining disagrees with stratified semantics on stratified programs. And this may be problematic in some situations because the stratified semantics is widely accepted for stratified programs. Forward chaining semantics is very simple to explain. It's purely computational. However, what programs do with forward chaining semantics may be sometimes hard to understand because what they do is highly dependent on the timing of firing of the rules. And we've seen that in some examples. In terms of use in practice, forward chaining is used in a limited but important class of applications, which includes some of the ones I previously mentioned: active databases, production systems, expert systems, workflows, and more generally, systems that can be viewed as data-driven reactive systems. So since the late 80s, the landscape of Datalog has become extremely rich and varied, as has the its applications. But I believe that forward chaining is likely to remain a useful alternative within this rich landscape of Datalog. Thank you very much for your attention.